anti-smoke dampers. It drives upwards through gaps and voids.
The smoke travels up into the higher levels of the building.
Almost all of the victims killed by poisonous smoke are at upper levels. Following the disaster, sweeping safety changes are rushed in across the entire state.
So just a few months after the fire, the state of Nevada changed their regulations, and they required now that all high-rise buildings over 55 feet would have fire alarms and sprinkler systems.
That included older buildings, like the MGM Grand. Just a year after the disaster, it reopens. It is now fitted with a fire detection system and sprinklers throughout the building, including the casino and the deli. The cause of this devastating fire is a fault that was out of sight inside a wall. And fire isn't the only lethal catastrophe caused by faults no one can see. Genoa, Italy. The colossal Ponte Morandi Bridge. Its most iconic section is a spectacular stay bridge.
Each stay section consists of a central pylon with two stays extending from either side down to support the road deck.
Stay bridges have been around for hundreds of years. But with just two stays on each side, this bridge is the ultimate in minimalist design.
The Morandi Bridge was designed by legendary architect Riccardo Morandi, who was Professor of Civil Engineering at Rome and Florence universities.
The landmark structure is a symbol of Italy's engineering prowess.
Morandi Bridge was perceived as a masterpiece at the time. It really changed the way how we looked into bridges.
On August 14th, 2018, an 820-foot section of this engineering icon collapses. More than 35 vehicles on the bridge plummet 147 feet to the valley floor. 43 people are killed.
The collapse shocked the people of Italy and across the world. How could such a marvel of post-war modern engineering fail in so spectacular a way?
Vital clues could help explain the deadly collapse.
We have witness reports, we have CCTV, we have maintenance records, and of course we have the original design plans for the bridge.
Using this evidence, we will digitally reconstruct the disaster to find out why it happened. One of the single most valuable pieces of evidence in the collapse of Italy's Morandi Bridge is this footage from a security CCTV camera on the valley floor. By chance, it captures the moment the stay bridge collapses. Zooming in and enhancing it reveals something extraordinary. The roadway on the far side of the pylon collapses first. And the stay supporting it is sliding down, which means it must have broken away from the bridge. Using this incredible evidence, we can reconstruct the collapse frame by frame.
After the first stay fails and the road deck starts to drop, there's a twisting force on the tower and an opposite stay on the other side of the pylon fails. The road deck now falls down into the river and onto the industrial buildings below. This entire sequence of events begins with the failure of a single stay.
How could the giant stay fail? Most stay bridges use visible cables or rods for their stays, but Morandi designs something that looks completely unique.
Morandi wanted to achieve a particular aesthetic where he wanted a limited number of stay supports.
So when you look into the Morandi Bridge, you think that it's made of concrete as a whole.
But this is simply a clever design trick. The cables are still there.
All the cables are hidden inside the concrete.
Beneath the concrete covering are 52 steel stay cables. 28 of these cables are threaded through a series of steel tubes, and then it's all cast in concrete.
This allows steel that would otherwise be exposed to corrosion to be protected by the concrete, which would be compressed and prevented from cracking, and that would deliver the aesthetic that Morandi wanted.
The tension cables in the tubes are secured by injecting concrete-based glue called grout into each steel tube. This provides a second layer of protection from corrosion. It is a carefully thought-through solution to protect Morandi's design from failure. But despite that, the evidence says a stay does fail.
Looking at the CCTV footage, you can see what looks like the initial failure in the southeast stay of that pylon 9.
For the stay to fail, the cables inside the protective concrete casing must have snapped, and that is backed up by key evidence.
Now, witnesses report a dull metallic sound as if something is snapped or broken.
How could these massive cables just break?
When they examined the sections of cable inside the conduit, what they found was about 20% corrosion. In other words, rusting was gradually thinning down the steel cable until eventually it was no longer strong enough to hold the load.
Corrosion causes the collapse that kills 43 innocent people. But the bridge design is supposed to protect the cables. How does corrosion get in? Morandi's design was supposed to wrap the cables in an impenetrable barrier of concrete. Something clearly goes wrong with this plan.
Analysis show us that there are large cracks on the stays, which when you examine from up close you see that they are dirty, which means that they were old cracks.
Other evidence suggests that these cracks were decades old.
Maintenance reports from as early as 1979 tell us that there were some cracking on the stays.
That means corrosive moisture may have been penetrating through the protective concrete barrier for nearly 40 years. But there's supposed to be a second layer of defense against corrosion, the concrete glue, known as grout, that surrounds each cable. Why does that fail? Why doesn't the grout surrounding the Morandi Bridge's stay cables protect them from the corrosion that leads to its collapse?
Evidence show that there were large gaps inside the grout that was poured inside the steel tubing that surrounds the steel cables.
How could these grout failures have been formed unseen beneath the concrete?
The problem with this second line of defense was that the waterproof grout was quite a thick mixture, so it couldn't flow freely.
So if you're trying to pump this grout into small spaces, that's going to be quite a hard thing to do.
What actually happened is that it then left gaps or voids such that the steel wasn't completely encased and protected.
Both the grout and the concrete failed to protect the steel cables. But even given the failure of both layers of protection, the level of corrosion is still extreme. What caused it?
Corrosion of metals occur because what they do is very slowly react with oxygen from the air. And in the case of steel, it's the iron which reacts with oxygen in the presence of moisture and acids. And what it does is it produces rust, which is much weaker than the original metal.
And chemical evidence suggests something made this rusting process that eats away the cables particularly aggressive.
Analysis of the corrosion in the stays suggested that it had actually been accelerated by an aggressive mix of water, of sulfates, and of chlorides.
Why is the environment so corrosive?
If we look at the location of the bridge, we can see that it's only 1.5 miles from the Mediterranean Sea, and this means there's going to be a lot of salt in the atmosphere, chlorides. And when steel is exposed to chlorides, it can cause the steel to rust, and that's really bad if you're steel that's making up a stay cable in a bridge.
Another issue is that the bridge is located on top of an industrial area, which, among other things, houses some steel recycling facilities. And those industries release a lot of airborne pollutants.
These pollutants can create highly corrosive acid rain. The Morandi Bridge is built in a chemically aggressive environment that eats away at any exposed segments of stay cable until they snap.
There are a number of things that haven't gone perfectly well with this bridge in terms of the grout, in terms of the corrosion of the steel and the stays. But there are many cable stay bridges in the world that suffer similar problems, and they don't fall down.
Is there something else beyond simple corrosion at play in the collapse of the Morandi Bridge?
Cable stay bridges, of course, were not a new idea, and multiple cable stay bridges existed around the world, but often these bridges had multiple stay cables on them, rather than a single stay.
If one stay fails on these bridges, there are others to take up the load. This is a critical concept in engineering design. It's called redundancy. It protects you from failure. Why doesn't the Genoa Bridge have it?
In order to achieve this aesthetic with few stays, resulted in a bridge that had essentially no redundancy. And so when the corrosion of the steel occurred and the stay failed, the entire bridge collapsed.
Losing redundancy is the price Morandi pays for his minimalist design aesthetic. It proves a catastrophic decision. The roots of the Morandi Bridge collapse begin 50 years before the disaster, with its concept and construction in the 1960s.
Because Morandi wanted to emphasize a simple aesthetic, he bundled all of those cables together into a single stay.
But the concrete that is supposed to protect the cables from corrosion begins to crack after barely a decade. The inner ground protection also fails. This lets in a corrosive chemical cocktail that eats away at the cables.
Eventually, the cables within the southeastern stay on pylon 9 snapped.
It triggers a devastating collapse that leaves 43 people dead. Just 2 years after the Morandi Bridge collapses, it is replaced by a new bridge.
Genoa St. George Bridge is not a cable stay bridge, it's a viaduct bridge. And indeed, it looks like the lessons around maintenance might have been learned, because the new bridge is even equipped with a series of robots to ensure that appropriate maintenance is performed.
Hopefully, the lessons learned from the tragic collapse of the Morandi Bridge will ensure a disaster like this never happens again.